I'm ready when everybody else is. If you want to find your seats, make sure you got your bathroom break done. Yeah, I couldn't help watching Robin's video there. I felt like, anyone see that movie Tomorrowland? With George Clooney, you know, Tomorrowland? There's a little kid who's a star in the movie, and she's going through class, and they're showing, here's the problem, here's the problem. She's like, how do we fix it? And I'm here to tell you how to fix it with Epic. We feel it's a tool that can fix a lot of the issues that Robin discussed in that keynote speech regarding green infrastructure and the solutions to be able to move forward. So Epic is an acronym, actually. We have our booth over here. Jonas, who invented the system, can tell you all about it. The acronym is Environmental Passive Integrated Conveyance. So we are a highly modified French drain, if you will, that has the feature of irrigation as well, too. But we're going to go over the filtration aspects of the Epic system and then how that functions. So before we begin, how many here are planners or, I know there's one planner, I spoke with you earlier. Yeah, see, you draw. Engineering background, any engineers in the house? Or architect's background? I know we got transportation over here. And how many are just here for the free lunch? Okay, we got a full crowd. It's applicable to everybody. So let's go ahead and move forward. So to start, I've got my first video here. This is actually our most popular video on YouTube. It's not even about our Epic chamber. It's about how French drains fail. So everyone's seen this type of French drain before. It's a slitted pipe in a rock environment. And if you hit play, we can see what happens in an environment where particles infiltrate into that pipe and block that conveyance. It's a common problem. Many golf courses would install these types of pipes and their bunkers would flood in the very same season. We actually helped replace all the bunker drainage at Sonoma National, and they're still not plugged like that today. So the solution they had is they would wrap those French drains in geofabric. And like, okay, that'll stop the particles from getting into the pipe and causing it further clogging downstream. But then if you leave your coffee filter on all week long, what's going to happen? It's not going to brew coffee anymore. It's just going to not get through the filter. So wrapping these pipes in geofabric is not the solution either. That's where the Epic solution is the answer. And here we have a quick comparison. As we hit play once again, where we compare our Epic chamber with that conventional type drainage. Just pour to its dome. So if you haven't gone to the bathroom yet, this will be your cue if you listen to the audio. But what I want you to pay attention to is the drainage rate in comparing how efficiently Epic can drain in comparison to that conventional pipe. And this is just in a 4-inch aquarium. Imagine 40 feet, 400 feet, 4 miles. The efficiency that we can be able to move and convey that water without ever clogging. And that's all due to the offset pole interface that we can really show you over there in our booth. It's always a relaxing video, this one. And this is available on our YouTube page as well there too, if you want to be able to watch it. And we even added orange juice to the water samples to simulate stormwater to get the particulates. So our idea of a road filter is, they slow it, sink it, and spread it. And so by having these type of filters on the edge of our road systems, we can be able to help manage the pollutants that are coming off our roadways and take advantage of that new water resource. So we already have the surface area, we already have the right-of-way and the shoulder. We just simply add this new feature. Roads have been around for a long time, thousands of years. The Inca road system in South America, Roman times there in the lower left corner of Pompeii. And then we've got our paved roads today of the 19th and 20th century. The paved surface, lane markings, rumble strips to help warn you that you're getting too far, shoulders that give you that extra room. And what we propose is the road filter to help filter pollutants and stormwater coming off our road systems, because we feel that that is a significant move forward to green infrastructure improvement. So what is the road filter? Well, if you look at the top, it kind of a system of our epic chambers, which are the interface with the subsurface gravel, that are connected in series with a 2-inch connector pipe. That could be PVC or ABS, Schedule 40, but that's kind of a fill and spill as you sequence through the process of that filter. So you have a 12-inch fine gravel layer at the edge of the asphalt, the edge of the road. That can be lined or unlined, depending on the native soils. I always prefer to try to line it if you can, because then you're hanging on to the extra water, and you're also protecting the subbase of the road itself too. By having stormwater go underneath the road, that can really cause potholes and different degradations to form in these roads. And so by having the transfer be below the subbase, you never have an issue of any water making it underneath the road base and causing those degradations that take place. So the water gets filtered down through the chamber and then can go out to a filter discharge or reuse. Now, the National Pollutant Discharge Elimination System has identified our highway system as a major contributor to pollution. And you think about it, where's all that pollution coming from? Well, it's coming from our cars, whether it's hybrid or gas or electric. We all drive on tires, and those tires have carbon black and tread and different brake dust and stuff that comes off these cars to be able to stop and go on our highway system. There's over 1 billion tires manufactured annually. And Jonas, just because he's a scientist, took a new tire and he weighed it. It weighed 30 pounds. He took his used tire before he got the new tire and he weighed it. It weighs 29.16 pounds. So we're losing that 0.86, 0.84 pounds per tire. That's over 3 pounds of carbon black that went somewhere on our road system. Where did it go? Well, in tread. And you'll see it on your driveway from time to time. It's microscopic, but it's there. And it's made of carbon black. We actually came up down here from Reno and Lake Tahoe. And around Tahoe, you'll see snowbanks in the wintertime. And that really gives a good reveal of what's happening down here by the coast and all around California and around the country, is that we are polluting from our roadways, from the carbon black coming off our tires. So we took a dirty snowball, we melted it down, and we went ahead and ran it through a filter. You can see the initial sample there, the black on the left is the initial filter with the carbon black particles and the sediment. The middle is the gravel filter, and the clean one is running through a sand filter. So just as we filter our drinking water through sand, we're applying that to stormwater management through sand filtration, aggregate filtration, and the microbiological degradation for the oil water separation, and even biofilters where plants can extract those micropollutants that currently aren't filtered by our current system. So you look in a microscope, there's those tire bits, those little tiny microscopic, 1/10 of a millimeter bits. But that's the micropollutants that make a difference. You look at the heavy metals are in that carbon black, but also look in the green. You've got calcium, iron, magnesium, phosphorus, potassium. Coincidentally, all the nutrients that plants need to survive and grow is calcium, magnesium, iron, phosphorus, potassium. Seeing a pattern here? So when we have these stormwater events, these contaminants or nutrients for plants then run off into our watersheds, and that's what helps contaminate these watersheds and ponds and detention basins and grow aquatic plants such as algae. Often to the point where they say, don't let your dog drink that water, don't swim in that lake because there's too much of an algae bloom. Our philosophy is if we can filter those roads and take that polluted, nutrient-rich water, now we can apply that to terrestrial plants and grow trees and flowers and shrubs and more aesthetically pleasing plants than algae and mosquito breeding pits. So another example of stormwater management, if we have clean water hitting our roof and hitting our road system, why are we just discharging it right into the contaminated waterways? Why not reuse it? So the beginning subtle effects of road erosion, may be subtle at first and obvious over time. Now, this is from my cousin's house in Washington State. So same 4-inch French drain pipe is used as their drainage. It clogged up, and guess what? The whole road eroded away. And there's the erosive nature of water. It begins with small little canyons, and we have in our standards in our books, straw wattles to help with erosion control. But the flows just build up and go around those wattles, and the kinetic energy continues downstream. So currently, we still aren't truly having solutions to the problem. You look at a typical curb and gutter installation, it's kind of dirty and mucky because it came down past the riprap, picked up sediments and debris, and it's all overwhelmed into a 3 square foot catch basin. That whole 400 linear feet, you have 3 square feet allocated for that drainage of that road curb. What if the whole edge of the road curb was your intercept? What if at the entire edge we had our epic road filter in the intercept through pavers, for example, at the surface, that then could be able to collect that water like they did here in Modesto for the Beckworth Veterinary Hospital. So instead of 3 square feet of openings, we have 23.6 square feet of openings just between the cracks of those pavers along the entire road edge. We're capturing it at the source, slow it, sinking it, spreading it out, calming down that kinetic energy and erosive buildup. Here's another example at the Nevada Department of Transportation where they were facing EPA fines for the runoff coming off their maintenance headquarters there. And so we installed the epic filter along the edge of their roadway, buried it with open grid pavers, along the edge of their maintenance area. This is where all the snow plows park and shed off all that stuff from working hard in the mountains. And here it is during a rainstorm. So they also installed this, they liked it so well at their NDOT headquarters in Carson City, they installed an SR28 to help keep that legendary clarity of Lake Tahoe for a BMP to help filter for the East Shore parking area. So all of the parking spaces, the drive lane, we'll show that in tomorrow's presentation, have epic underneath, and so that saves the real estate. You don't need a storm pond, you're driving over the storm pond. It's that gravel with the pavers on top. So everyone knows that oil floats, right? It's less dense than water. And so by that, we actually have a natural oil-water separation. If you look at the fundamentals of the chamber, it has offset holes. So the water comes into the chamber where the yellow line is, but it doesn't leave the chamber until it fills up to the blue line. So if the profile is filled to the blue line, the oils aren't going to be able to make it into the chamber and flow out to the outfall. So that way the gravel gets coated by the hydrocarbons and the oils and the yuck for microbes and bacteria to be able to then break down those hydrocarbons back into CO2 and water. And it's that natural decomposition that takes place. The BP oil spill in the Gulf years ago was a huge issue. They thought, my gosh, what a natural catastrophe. And after a short while, they realized that, oh, it's not so bad after all. And what occurred was there was bacterial blooms that then consumed that pollution because it became food for the bacteria. So there's good bacteria that helps us out and helps save the day and works nature's course. Otherwise, we'd be inundated with leaves if things didn't decompose, right? each fall. So this has led to, and we have the full standards there at our booth, the Los Angeles Bureau of Engineering and LA Sanitation standard plans for a street road filter. If you do a Google search or any kind of search for LABOE S400 series, you'll see their Green Street standards, of which this is standard 495. And it's a shallow catch basin that captures the runoff from the road. And it has a monitor there you can see on the elevation view, so you can take samples and double check as you go. And that can then just connect directly to a storm drain just downstream. So now we can apply a filter to our stormwater system and at least have that hydrological responsibility of filtering it before we let it get into our conventional storm drain system. So you have your online and your offline system. If you look at the top text there, we're still going to have flood control as the civil engineers design, but we can have this offline system that can help filter and slow it, sink it, spread it, and control those stormwater management pollutant influence into our local watersheds. And this is a top elevation view. Again, that comparison. We have 3 square feet of openings versus 23 square feet of openings on that paper space. So the standard, and if you look it up, it also has different tables of the spacing for different streets, the widths, and that sort of thing. But it could be just one small catch basin upstream or the entire edge of the road. Let's see if I can, so that's basically the drainage, the filtration part. That's the first of 3 I'll be showing you in this presentation. This is an introduction to the second part where we reuse that is stormwater.
Introducing EPIC, the Environmental Passive Integrated Conveyance. It is not merely a tool, but rather a revolutionary technique that brings about a paradigm shift in water infrastructure management and design philosophy. For 25 years, EPIC profiles have undergone continuous innovation and development, resembling the strategic construction of stream embankments. These profiles are engineered to optimize passive irrigation through leveraging gravitational forces and capillary physics, thereby achieving a remarkable 100% water use efficiency. The capillary movement is dynamic within the EPIC system. Using the shallow profile depth of up to 60 centimeters, depending on local approved sands, there is more water at the bottom of the EPIC profile, and you therefore have varying moisture and oxygen ratios at different levels of the profile. As such, the EPIC profile empowers plants to establish their preferred root zones, according to optimum ratio levels of moisture and oxygen that they require in order to thrive. The EPIC sand hydroponic apparatus and method is a breakthrough technology that for the first time, civil engineers have a self-performing, reliable conveyance tool that enables the subsurface distribution of liquids and air in a three-dimensional engineered aggregate profile. EPIC chambers are used individually or connected serially in preformed cells of fine gravel and sand. The EPIC solution is modular and scalable, that can have a multi or single function at the same time. EPIC has many features and benefits, but here are a few notable ones when deploying it for irrigation. The EPIC system has a lifespan of at least 50 years and requires very little maintenance. The system can be installed in remote areas and can operate using a submersible solar-powered pump. EPIC can save up to 85% in water use compared to traditional irrigation methods. It can achieve net zero water and maximize greenscapes. EPIC can help save up to 40% in fertilizer use by applying nutrients through sub-fertigation. It drastically reduces plant diseases and minimizes insects. People can enjoy their time at a park where they can comfortably sit on the grass without having to worry about dampness, because with EPIC, the surface of the profile is dry, while the roots are taking in their nutrients silently below. It's time we embrace a new philosophy for water management with EPIC Total Water Solutions.
And credit to my colleague Robbie, who's watching on the Zoom link from Dubai right now. He's working on EPIC systems in the Middle East with all the green infrastructure going on over there. So, of course, for the conservation reasons of just using 50 to 80% less water than sprinklers or drip. And that's because we have a liner. We don't let the water escape into the ground. We use every drop within the profile. So this is recognized by the City of Los Angeles for their Low Impact Development Handbook, which happened to be published on my birthday on May 9th. I was really stoked about that. And so that they call it capture and use down there. And essentially they're required, and this is the kind of policy that I think all municipalities should consider, is that 85th percentile at minimum is required to be captured and reused on site. So whether you're building a little shed or a whole skyscraper, you have to prove to the city and submit to their LID counter that you've accounted for that stormwater to be captured and reused on site somehow. And EPIC is one of the tools approved to perform and meet that regulation. So when you look at all the dirt in the world, the clay, the silt, the loam combinations, the sand, our exclusive choice is sand. And the reason for that is that it's a very reliable medium. The aggregate is it's crushed rock, usually 1 to 2 millimeters in size. And you can kind of see it's like a miniature boulder, and there's void spaces between those boulders, where if you look at clay in the lower left corner, those are more of a platelet type formation that gets so compact not even air can fit in between. That's why you see trees suffocate, because their roots are getting compacted, like it's hard to sidewalk, the dirt. But where sand, it never overcompacts. And we use a 1 to 8 particle ratio for our bridging layer, or choking layer, and that's where you'll be able to see that the sand particle is 8 times smaller than the gravel particle. That way the gravel allows the water to spread laterally on top of the liner and then wick up into the sand profile like a sponge, if you will. And this is another quick little video that just kind of shows that bridging layer. Let's see if I hit click if that works. No, oh well, we'll just skip past it, it's all good. But this is an illustration of the capillary rise and how the adhesion-cohesion properties of water allow that capillary rise to wick in between those sand particles. Has everyone ever seen like a glass full of water and how it can get just above the glass? When you put a straw in that glass, it'll be a little bit higher in the straw, and that's the fourth state of water. We've got solid, ice, liquid, water, vapor, gas. What's the fourth state? It's the water film, the surface tension. That's what allows that capillary rise to take place. Now this one I do want to show you, because this is a really cool 6-hour time lapse of capillary rise of us introducing water into the profile there. So you can see the water does wick up. It does take time. It's putting the excitement of watching grass grow or watching paint dry, but it is reliable, and it will always occur in medium wash sand profiles that are locally sourced. We find the same the same sand used to make concrete is what typically is going to work in an EPIC system. You wash masonry sand, wash plaster sand, and these are available locally, and it helps you earn lead points and that kind of great stuff. But it's lets the plants decide how much water they want to take. If it's a cactus or a sedum, they'll have very shallow roots towards the surface where there's more oxygen and more air. If it's turf grass or a strawberry, they'll dive real deep and get deeper roots. You're looking for that moisture down below. And so you let the plant become the ET calculator as the plant decides its root zone. Now you can be able to see the offset holes between the chamber and the saturated zone. That's how we interface without ever clogging. So we have that conveyance, that path least resistance to the chamber. It wicks up into the capillary zone, and that is the ideal growing environment for all plants. They have both oxygen and moisture available to breathe and drink at their discretion. And then with the predictability of capillary rise, we have a dry crown, so it helps reduce unwanted species from germinating, weeds blowing in on the wind, that sort of thing. And so there you can be able to see the roots growing around the structure of the chamber. Notice the date. We've been doing this for a long time, over 20 years. And 20 years ago, I used to fit those pants. But you can see the root growth is phenomenal in these EPIC profiles. And why it's phenomenal is because the plant can decide how much moisture, how much air, how much nutrients it wants to uptake at its discretion. Notice the picture on the left is from top watering, and that's the shearing, cutting action, the water rushing through the profile and damaging the root hairs, where the slow movement of capillary rise in the right, you can see a stronger, more prolific plant system. So that we get twice the plant growth with half the water. So that's just another expanded view of kind of the components of the system. It's very simple. The toughest part is the level subgrade. We operate by gravity, so we want to level off that subgrade. Then you line it with the water barrier, EPDM liner, the sequence of conveyance chambers, and the gravel and sand layer. So this entire yard is all within EPIC. The pavers, the turf, the trees, the shrubs, the flowers are all within the same system. So it doesn't have to grow. You can have sidewalks and pavers and parking lots over EPIC as well too, but it functions as that stormwater management underneath it as your base. So this entire backyard is all irrigated from a small pump about the size of my fist that operates off an electrical timer, similar to when you go on vacation and you have your lights turn on automatically. The timer kicks the pump on once per week for 24 hours. That's all we need for our irrigation duty cycle. Once a week it kicks on and recirculates, pumps water away from the pump, it flows by gravity back to the pump, and then just keeps recirculating until the system is charged. And that's enough to keep the plants happy. It holds 2.5 gallons per square foot, like a wet sponge, if you will. So there's kind of what the liner looks like. And notice the roof downspout connection, because that roof downspout is the water irrigation source here at bicycle parking in Minneapolis. There was one drought where they stuck a garden hose down there because it got a little dry. But past that, the rain keeps that irrigated. There's no pressurized sprinklers or drip. It's all by gravity. So in this case, the water pumps up to the taller grasses, flows down to the turf, and then back to the vault there again. There is another pipe as well too for an overflow if it rains a lot. That way it's not a closed system. You still have an out for that filtered discharge. Any size or shape can be accomplished. Just notice how the roof downspouts are always connected to the system. Sheet flow, always directed towards the system. So instead of that mosquito breeding pit or detention pond, now your landscape is your detention pond. Your landscape is your stormwater management. So it's a dual purpose in accomplishing that green infrastructure. This is a house just up the way in Palo Alto. It's the Cisco, was that? The executive from Cisco installed that right by the infinity pool. It's a really fantastic installation. But yeah, it's not just turf. All plants can grow in sand. Your trees, shrubs, This Chinese maple was planted in a 13, 14-inch profile. Within 7 or 8 years, it was a huge caliber, like 7, 8 inches thick. It's a massive tree. And so, this is the Da Vinci 5th floor luxury apartments in downtown Los Angeles. The trees, the shrubs, you notice there's an elevated profile to accommodate the bigger tree root ball. Each one of those palm trees was $10,000. The landscape architect was concerned, like, gosh, is it going to make it in wet sand? And they did just great. You can also plant trees adjacent to the system. So the capillary rise goes up over the wall and into the tree root ball, where those at TCS Stadium in Minneapolis grew prolifically and still are growing right today. Also, the turf is reinforced with a different product they'll be showing you tomorrow, that the media trucks park right on the turf as well too, and have that access like a green fire lane. So here's a school in Sacramento. This shows the, you can see the maintenance building up there in the corner, where we have a 3rd horsepower pump that brings water to the closest edge, or the inlet header. It then flows across the field to the far edge, so that's where the drain header is, and that drains back to where the pump is. Oops, what happened? What did I do? Shucks. It's getting right to the good part. Did we lose battery? There it is. Okay, hey, it's back. So you can see from the inlet header side, the moisture as it's wicking towards the surface and creeping across the field, making it to the drain header side. We germinated Kentucky bluegrass. It germinated in 8 days. Here it is at 20 days. Edge-to-edge germination, even though it's windy up on that hill, no hot spots whatsoever, because all the moisture is wicking up from underneath, never surface water. Here it is at 45 days, 4 to 6 inch root growth, and it's ready for its first haircut. So this is where the money savings of green infrastructure can take place, because this particular field saves $700,000 from their water connection fees. For sprinklers for this field, they need a 3-inch line, $750 grand. For Epic, we only needed a 1-inch line, which is $50 grand. So it essentially paid for the field before it's even built. And so that's another aspect of savings utilizing these types of green infrastructure solutions, is that you can save real estate, you can save water connection fees, and you can save on grading, because it's all level grading areas. For climate resiliency, this is a field in Dallas, Texas at SMU, one of the only playable fields after a hurricane. Equally, on 100 days after temperatures over 100 degrees, the field is still able to conserve enough water to look great and function well. So whether it's a very wet climate or a very dry climate, the system is adaptable to those conditions. Agriculture, another thing I wanted to touch base on. This is a greenhouse in the United Arab Emirates in Al Ain. Gets hot there, I'll tell you what. I was working in 120, 130 degree heat. We take a break between 1 and 4 p.m. because it's just unbearable. But the cucumber growth we accomplished with the state-of-the-art drip system got 300% the yield. And that's because of those cucumbers can be able to take exactly what they need when they need it. You can see the drip on the left and the Epic growth on the right. This is a greenhouse in Nevada in partnership with the Future Farmers of America, that we help to educate students on futuristic ways to grow plants. And there's our first tomato harvest that went to local food co-ops and grocery stores in the Rayleigh's grocery stores there up in Reno. So for the engineers, the absorption dynamics, it can be really fun math. It can build the fun back into you can be able to see the infiltration rate, capturing water from the street. We know the transfer rate through the 2-inch pipe is 20 gallons per minute. We know the sponge holds about 2.5 gallons per square foot. And then the evapotranspiration rate. Since it's lined, we can meter that and know exactly what it's going to be. It's about 0.15 gallons per square foot per day up in Reno. Down here at the coast, maybe 0.1 gallons per square foot per day, because it's it's more humid with the fog rolling in, that sort of thing. So this then led to the second portion is the passive irrigation. So this is the Stormwater Green Infrastructure Design Standard Plans. This is standard S496 with Los Angeles, where now that we've captured water from the streets and we've filtered it through the road filter, what do we do with it? Well, now we can reuse it in passive irrigation in the parkways and the medians and in adjoining parks and strategic areas. And maybe you have nuisance water in your local community that just keeps flooding across the road. Like, well, this is where you can now build a park by that nuisance area. Or the standard plans exist, and they're public information for you to copy and paste and take it as you please. Most streets have a slight slope to it, and we're operated by gravity. Well, how do we accommodate that? There's a level subgrade that is then benched and segmented down the slope of the street. And it all recirculates by a solar pump. So every 300 feet can be recirculated by a solar pump, but then the drain can still connect on down the infrastructure system. So getting around trees, you might have existing trees that you want to be able to irrigate with this. You simply can build around the sidewalk, and the flow pattern can become the base of the sidewalk, yet the trees still can take from that sand profile as an irrigation source. So we can be able to retrofit older or build with new. And my favorite part, this is the third component and the most exciting aspect, is full sustainability. We already have the road surface, we already have the road filter. Why not add storage in the right-of-way? The government already owns that land. Why not have a linear reservoir system to where we can capture the winter rains and reuse through the summer? And now these systems can sustain without the need for a pressurized city water supply, without the need to drill a well, without taking from the groundwater. Let's let those ancient aquifers stay there. We can supplement with what precipitation falls upon the project site or upon the cityscape. So now this expands our basic schematic to not just the road filter, but reuse in the right-of-way as well too with these storage components. And this has been accomplished, this has been done. You start thinking about the numbers and the math of it. We're only taking a pencil line of a road. The infiltration is still going to occur in the mountains and then make its way down to the ground aquifers, but why not take advantage of this water resource that's falling upon our road system? We envision that all roads could be green infrastructure, to where you have trees and landscapes and parks could be irrigated from the water that falls on the road. You start looking at the math, your first acre foot of a multi-lane highway is in the first mile of capture. You start looking at 100 miles at a time, you got 2,000 acre feet a year of free water that right now just sheds to the side, evaporates, becomes rain in Boston. Why not hang on to that water and reuse it? You look at hardscapes of cities, Albuquerque, Los Angeles, over 396,000 acre feet each year that just flows to the ocean, wasted. Why not utilize that water? You look at all of California, almost 1 million acre feet a year falls on all the roads of California. Why not implement some of these systems? And you don't have to do the whole state at once. You start with strategic low spots or water nuisance areas you want to be able to build a park, and you can connect and segment these types of systems on from there. Even in the worst case scenario where we're from in Nevada, the driest state in the Union, still over 85,000 acre feet annually hits those roads that right now just grows a sagebrush or evaporates. So why not be able to reuse it? And there's just one last slide to kind of conclude and then summarize the road filter reuse concept that I presented here. want to not take more from our groundwater. We want to give it a rest and stop taking so much from our groundwater and sinking California as it's been sinking for many years in the Central Valley there. Why not start to reuse the precipitation that falls upon our projects, and that way we can let the groundwater be at rest. Any questions? I really appreciate everyone's patience doing all the slides there. Yes?
So at the school in Folsom, where did the water come from? There was a 1-inch domestic line that was just an irrigation, a subsurface irrigation system, or was that rainwater? Because there's not much rain in Folsom.
Yeah, it's a combination of both. So the water connection was to a purple pipe, a Title 22 recycled water source. And that was that $50,000 water connection fee. So that connects to a tank that has a float valve. You think about like our toilet tank. Once you flush, the float valve brings it back to a certain level. So in that tank, it maintains that level. And then when the pump kicks on a timer, then the water level goes down as it's pumped out and recirculates through the field.
And then in the wintertime, or in the fall when it rains,
then it falls upon the field, and then that water is captured and utilized. Yeah, so at Folsom, for example, they didn't put extra storage underneath the field, but there are other fields that I'll be showing tomorrow as well that that are completely sustainable from rainfall events.
Now, isn't there a school in Cambria?
That's correct, yes.
Can you tell us a little bit about that one?
I'll be showing that all tomorrow too, yes. In that case, that school was installed up on a steep hillside, so they couldn't provide enough water pressure to supply sprinklers to that school. It's about a 12-acre campus. So we utilized water capture down the slope into strategic areas, from runoff down the slope, from parking lot areas, from roof areas, and that all went to 1.8 million gallons underneath the main soccer field there. And that's what's utilized. So they did meter a small line up for drinking water, that sort of thing, and for some of the landscape use, but the landscape portion has never spun that meter in over 20 years. Yes? Yeah, it's a medium washed sand, so washed concrete sand, washed plaster sand, washed masonry sand. Like I said, similar sands that are used to make concrete. And then the reason that we're looking for a washed sand is we want the fines, the silts, the clays to be washed out of there, so it's just the sand particles. And that's what allows that reliable drainage and reliable capillary movement. So we do approve the local sands being utilized. We actually have a installation with the State Department overseas, and they took a sand sample from the river embankment and they shipped it to us, and we're able to approve and determine that it's a 13-inch profile for them. Sometimes it'll be 14 inches, sometimes 15. In Dubai, in the Middle East, their red dune sand, smaller spherical particles, but their profile becomes about 24 inches that the capillary rise can go up. So it'll vary on the local approved sands. Is anyone else ever seen anything like this before?
So in the diagrams that you showed, there's one actually just below the E in Epic there. The spacing looks much more than what I expected. What am I looking at there?
Yeah, that's the chamber density can vary. So the more dense the chamber configuration, the more drainage capability it has, and the recirculation capability. But one chamber per 100 square feet is about the average installation for athletic fields and for irrigation purposes. But it can vary, and it's a little bit different than some of the other chambers that you've seen out there. Like there's Infiltrator and StormTech and Contact, that sort of thing. Most of those are for detention, and they're larger size. So they're trying to have a place to put stormwater and let it infiltrate and go away. Where we're having much smaller conveyance that we try to manage that water instead of move the water. Does that answer your question on the chamber density there, or do I need to extrapolate further on that?
Well, I would, yeah. You call it density, I call it spacing.
Sure. Yeah, so in that case, you can see,
So those chambers are not storage. The storage is a separate type of chamber?
Correct. It's the storage in the chambers, in the large chamber it's about 6 gallons, in the small chamber within the void space inside maybe 1.5 gallons, 2 gallons. The real storage is in the sand particles, in the void spaces. So that's where the sponge comes into play. That's the 2.5 gallons per square foot in the sand profile. But then you start going to the hydrochamber, like the Triton and the Xerxes, and the ones like the green ones that we were showing there at the end of the presentation. And those are 90 gallons per linear foot. And then you have a 40% void space because they're buried in gravel. So that's where the additional supplemental storage is to the profile storage, the passive irrigation storage. So when we charge an EPIC system, when we charge it for 24 hours, that's enough to keep the plants happy, depending on the climate, for a couple weeks. So that's why we charge it once per week, that no matter how hot it gets, 100 degrees, 95 degrees, it'll be enough to make up that evapotranspiration loss.
You're just going basically almost to field capacity?
Correct, yeah, so we charge the field capacity each time. And field capacity holds, during a rain event, about 4 inches of rain. So typically when we're charging about 3 inches, the first 1 inch rain event will be absorbed by the system before drainage mode engages and it starts draining out of the system. Like that sponge, like I mentioned.
And a lot of soil moisture sensors involved?
No soil moisture sensors whatsoever. We did work with some moisture sensors in the past, and they tend, due to the the electricity in the ground, the geoelectric circuit, you have different conductivity in clay soils as you do in sand media. And so we found that the moisture sensors were not calibrated properly that are available in the market for sand profiles. And that's where we went to the recirculation concept of, whether it's in the Middle East and hitting 120 degrees or here on the coast and having that nice 70 degrees. By recirculating once a week, you can supplement exactly what the plant needs. So the plant becomes the moisture sensor. The plant is the ET calculator that it simplifies all the complex electronics that are often involved with pressurized systems and sprinklers and drip.
So you're not monitoring the moisture in the soil per se. You're just looking at the plant material and saying.
Yeah, the observation and the monitoring is part of the maintenance duties of knowing which day they're operating their pump and having a peak like, yep, pump's working. It's going to made it to the end drain, and we know through nature that the moisture will make it to the surface.
And you have meters on it, measuring?
Yeah, we do measure the supplemental water meters, so those comparisons can be. That's how we get our data from comparisons to standard conventional drip and sprinklers. There was a study that's on our website from New Mexico State University from 2001 to 2004, comparing golf course screens with USGA standard sprinklers and drip systems, thoroughly tuned and to the best of the golf course does. And they found that not only do we have better turf quality in EPIC, but we use 70% less water. And that was in Las Cruces, New Mexico, where it reaches over 120. So. And some golf courses said they wanted to see it in many golf courses for 20 years, and now it's been 20 years, so we're gonna have to go back to the USGA and say, hey, it's still working. Start speccing us more.
Are you fertigating in the system? Or?
That is correct. Yeah, fertigation is an option, and it is utilized to where you add fertigation to the supplemental portion, not the recirculation portion, because then you can get too much nutrients. But yeah, very good question. You do add fertigation subsurface, but you also can do it traditionally on the surface with the time-release granules, because the morning dew and the wet sand moisture reaching to the surface is enough to be able to break down those time-release granules and still add the nutrients from the surface as well. Or you can do a combination thereof. So subsurface fertilization, fertigation, or surface, traditional. But the balance of nutrients is the most important aspect we like to encourage, and that's the Hoagland solution that was developed from Hoagland in 1938 in Stanford. And they grew many, many different plants to their optimum, and they picked the best ones and they burnt them and they analyzed the actions, and that's how they determined the 8 macronutrients that all plants need to survive at their optimum. The manganese, the potassium, calcium, iron, nitrogen, nitrate. And by having that balance of those 8 macronutrients, that's what we have recommended to maintenance programs to get that chemical analysis of their sand once or twice a year. And that then kind of tells them what to add the next season. Similar to golf courses in NFL and MLB, state field stadiums do. We've kind of turned into like agronomists just by being in this industry, because you will have customers like, what's going on? Like, it looks like you need some more iron. It just becomes inherent. You start looking for it. Aeration is still key. Just like Robin said, maintenance of these systems is still at paramount. You should encourage the clients not just to have the budget to install green infrastructure, but also include the budget to maintain that green infrastructure. It's not worth having, it's not worth taking care of. So making sure that you have a maintenance crew, that they have a mower, that they have the nutrients to add, that they have the maintenance staff to take care of these BMPs as we install them, not just set it and forget it. Although with that, especially with the drainage portion, you pretty much can kind of just set it and forget it. But when it comes to the plants and maintaining what's growing in these systems, like all living creatures, they do need that tender loving care. Anyone else? Any other? Yes?
Yes, I mean, it is always typically require some sort of annual maintenance. Do you guys provide manufacturer maintenance recommendations, or how does that kind of work with the
Yeah, we do. We have standard maintenance manuals that are available through our website, and we have project-specific manuals as well too, where often there'll be a Epic TWS technical advisor offering technical support, assisting the winning bid contractor on these installations to make sure if they have any questions, it can will be available to be able to help answer those questions. And then we can utilize those installation pictures as part of that project-specific installation manual to help maintain these systems in perpetuity. We just came back from the Microsoft Silicon Valley campus, and they changed their maintenance crew, so we had to kind of re-educate them on the process. But we make ourselves available and travel to these sites when available. We can always be able to reach out to us as well too. But much is provided in information that can be kept at the project site. And like I said, I'll be having some other great examples tomorrow in my presentation as well. And Jonas, the inventor of the system, has all his science there at our table as well too. If you really want to get to the nitty-gritty of the chamber and then how it functions, how those offset holes are really the magic that makes that interface function of not just the conveyance of liquids, but also the conveyance of air. You can start asking us about energy savings and how we can be able to make a thermal comfort zone and wafting air through pavers and that sort of thing. We've got great information we can be able to share with you over at our booth as well too. But I did notice that they have the food out. I'm sure everyone's getting kind of hungry, right? So any other questions, just feel free to come by our booth as well too, please. Thank you very much.
Thank you so much, Tomas. That was amazing. Can you imagine? I feel like the opportunities are limitless.
There's a lot.
So thank you.